I'm Dr. Massimiliano Galeazzi. I'm from the University of Miami in Coral Gables, Florida. I'm originally from Italy. I came to the United States about 20 years ago. I got my PhD from the University of Genoa in Italy, which is the city I was born. And then I moved here for my postdoc at the University of Wisconsin, spent a year at the NASA Goddard Space Flight Center, and then I moved to the University of Miami, where now I'm a professor in the physics department. Right now, we are in what is called the vehicle assembly building. So that is the first stage when we move here to the range. We ship all our instrument and all the other components of the payload. They are broken apart and they are shipped over here. They were tested at the NASA Wallops Flight Facility in Virginia. And once they're tested, they are boxed and shipped over here. Specifically, the purpose of what we study is look at what is called the diffuse X-ray emission. So if you look at the sky at night, what you see is a dark sky with bright point objects. Most of them may be stars, some of them may be, if you have a telescope, you see that are galaxies, a group of galaxies, or other complicated objects. If you look at the sky with an X-ray telescope, what you notice is that you have the same objects, but you also have a diffuse glow that permeates the whole sky. And essentially, the goal of our mission is to study some of the sources of that diffuse glow. So we know the sun essentially moves in our galaxy. And as it moves, it's like when you drive your car with the windows down, you get gas in the solar system. So what we are looking at is the interaction of the solar wind with the gas in the solar system from white sands. And the result from 2012 were actually, we showed that indeed we have this local hot bubble, that we demonstrated once for all that we are within this large supernova explosion that happened 10 million years ago. X-rays from space do not penetrate Earth's atmosphere. So to study them, you need to go at least above 160 kilometers or 100 miles above the Earth's surface. So the only way we can do that is either a sounding rocket or a satellite. And obviously, so a sounding rocket has the advantage that is not as expensive, but you only get about 5 minutes in space. So you need to be able to do your science within 5 minutes. A satellites stay in space for years. On the other hand, the price tag is much, much larger. So there are X-ray telescopes in space right now. We use them for our research, but for this specific research, there wasn't any satellite in space that we could use, so we are using our sounding rocket, and we design it such that in 5 minutes we can get the data we need. So for this mission, the primary data just come from the rocket and instruments that are on board the rocket. What we will use to interpret the data, we will use data from the ACE satellite, which is the satellite that measures the properties of the solar wind, so that will allow us to determine what's happening and extrapolate the physics of the solar wind charge exchange and how it will help us interpret the data. We'll also use other instruments like ground-based cameras, but mostly for go, no-go condition, to determine whether the conditions are appropriate to launch a rocket or not. The countdown is basically how we get ready for launch. For this mission, our countdown starts at T-4 hours. So at T-4 hours, we come here and we get the payload ready for launch. We need to make sure our instruments are working. We need to make sure that the telemetry is working. So we'll do a dry countdown run without really launching, as soon as we can. After that, we need to arm the motors. Basically, there are safety around the motors, make sure that nothing happens. But when we're good to go, we'll arm the 2 motors so that they're ready to go. After that, we need to remove the shelter. Right now, the payload is inside a shelter so that it stays warm. We'll remove the shelter and we'll raise the launcher so that we are ready for launch. When we are ready for launch, we'll do another dry run, a dry countdown, make sure that everything still works. Finally, we are ready to what is called the hot countdown, which is the last 10 minutes. And basically, we go through the instruments, make sure everything is working. We turn on everything that needs to be turned on for launch until we get to T equals 0, which is basically when it takes off. If we start from the back, the big section, which is the 22-inch section that you see down there is the DXL instrument. So this is our primary instrument, and this is the one that will give us the primary science. If you see, there are two big doors. So when we get in space, those two doors will open and will expose our instrument to the sky, and we can basically make the observation. Then we have the conical section that goes from the 22 inches to the standard 17 inch. Is telemetry. Basically, it controls all the electrical power in the payload, and it's also used to send the data to the ground in real time. This section here is UXT, which is the secondary instrument that we're flying. Again, you can see from the top that there are two doors. Right now, the two sections are not aligned. That's why those point sideways and these point up, but they will be co-aligned, and they will be observing the same part of the sky. The front part is more NASA engineering, has to do with the parachute is in the cone and other controls for the payload when we launch. And here we have our controls. So what you see here is what we will use when in the countdown. So the rocket launch itself is about probably 10 minutes. The first couple of minutes are used to take us in space. Then we start doing our real observation. And we have about 5 minutes in outer space where we are observing the extrasolar object that we are observing. After that time, we close our door, we get ready for re-entry. So we impact the atmosphere, we come back. When we are back within the atmosphere, the parachute opens, and then the payload gently, or somewhat gently, lands back on Earth. We will be able to determine whether a launch is successful or not almost in real time, because we will get data from the telemetry in real time, and they'll go directly to our computers. So we'll immediately know roughly whether the data are good, and they will be able to provide real science. It will take months to really do a complete analysis and publish the results, but I'm hoping that almost in real time we'll be able to determine whether we'll get good results or not. There are two things that I find very exciting about this mission. The first one is obviously the science. That's what I study, I know, and so this gives me the opportunity to know more about this object and increase the knowledge that we have of the universe around us. The other thing is more on a personal nature. I really like to go on a rocket campaign because of the people I meet and the people I interact with. So far, for example, when I was at White Sands Missile Range, we work with NASA engineers, NASA personnel, the Navy supports us, the Army is there to support us. And here at Poker, the same thing. We have people from the University of Alaska, people from NASA, so people from quite different backgrounds that support us, and I find it very exciting to get to work with all these people, know their different background, and be able to work next to each other to get this mission going.